So good afternoon. Welcome to today's webinar. We are pleased to present this series of SPE webinars, and our presentation today is being presented by Rajan Shotsky. This is a series of SCA webinars that we've been able to present, and today's webinar is Artificial Lift Challenges in Unconventional Reservoirs. The material that Dr. Shotsky will be presenting today is related to the experience that he's gained in his career. And you can see he's worked with a number of different companies, including ONGC, University of Tulsa, and Weatherford. He has experience as a petroleum engineer, in research, software development, and in business. Specifically, he's been involved in the areas of multi-phase flow, artificial lift, production optimization, and well performance improvement with real-time production monitoring. He has years of experience in teaching courses and workshops around the world in both public and private forums. He's worked in teaching at the university level, and he's also been involved in developing digital content for various industry experts. Dr. Shotsky has also served as an SP Distinguished Lecturer and chaired artificial lift workshops. He's been involved in global committees for SPE, so we're pleased that he's able to join us today. This webinar relates to the class that Dr. Shotsky presents for SCA on artificial lift and real-time optimization for unconventional assets. That's scheduled in public sessions in March in Houston and in October in Midland. And it's also available for in-house classes. So if you're interested in either the public class or scheduling in-house training, please contact SCA at the information provided below. This is part of the webinar series that SCA has been offering, and going forward, we expect to see Dr. Oscar Lopez-Gamonde on kinetic sequence stratigraphy, Leo Roadhart and Garrett Nitters on well stimulation, and John Lorenz and Scott Cooper on natural fractures and controlling reservoir permeability. So we look forward to seeing you at some of those upcoming events. Of course, SCA, in addition to training, provides consulting, direct hire, and projects and studies. So as part of our webinar today, we would like to conduct some quick polls to learn a little bit about our audience before we start. So please give us some information on your primary discipline. And looks like we have a number of people involved in reservoir engineering and geoscience, no surprise, but also several involved in production and operations engineering. And we have a few in the drilling and completions category and a few in production facility construction. But I'll go ahead and close the poll. We almost have all the votes in. And it looks like the majority are either in reservoir engineering, in geoscience, or in production and operations engineering. So the next polling question is, how many years of full-time experience do you have? And I'd like to see what the spectrum is of various attendees at today's call. And it looks like we have a pretty wide group. The majority is in the 11 to 20 year category. But we have quite a few with over 30 years. So we've almost got everybody's votes, so I'm going to go ahead and close that poll and share the results. And then I'm going to go to our next question. And how many years of experience do you have with artificial lift? Since that's the topic that we will be discussing today. And looks like we've got a lot of experience in this crowd. Pretty good distribution among all the different categories. So we've almost got all the votes. So I'm going to go ahead and close that and share those results. And it looks like the most are in the 1 to 2 year category, but we do have a pretty good distribution in all the other categories as well. And last question, in what type of reservoirs do you work? Either conventional reservoirs, unconventional reservoirs, or both? And looks like we have quite a few that work in both types of reservoirs. The vast majority, I would say, have experience in both types of reservoirs. We've almost got all the votes. So I'll go ahead and close that question and share the results. And the majority of you work in both types of reservoirs. So I'm going to go ahead and give the presenting rights over to Dr. Shoshki. And let me, let's see, Joseph, can you help me with that, please? As far as handing over presenting rights?
Yes, I'm working on that.
Or am I going to show the slides from here?
I guess you're going to show the slides.
Okay, I'll go ahead and do that. So let me pull out of this slide presentation, and we'll move into the presentation here. Okay. All right, take it away, Rajan.
Okay, Susan, I don't see the slide here, so okay, there we go. Thank you.
Okay.
Good afternoon or good day to all the present on the webinar. Thank you for your interest and participation today. The talk I'm going to present in next 40 minutes or so will cover the following topics. After a brief intro to what is an artificial lift, I'll try to point out how the lift application or production space itself is different for unconventional or tight wells. Actually, I should say that for horizontal wells, right? And we'll focus on two aspects: well geometries and flow behavior. And then we'll talk about some of the field practices that have worked with some case studies. And a couple of takeaways that I would like you to leave from this webinar, are the importance of lift life cycle planning. And we as an industry, we are also realizing that we need to be doing this not only for unconventional, but for conventional wells as well. And second important aspect is the optimization, monitoring, and surveillance of not only the lift, but in general, the production profile of the unconventional wells. And we'll conclude afterwards. Next slide, please, Susan. So when you go to the artificial lift application space, and this graphic shows World Oil survey that they represent almost every year. And from a couple of years ago, they showed that for past 10 years or so, the number of wells in the United States on artificial lift, that ratio has remained at about 95% of the total producing wells. And in my estimation, this ratio might have increased a little bit because unconventional wells, the number of wells that have increased in past few years, most of them end up on artificial lift sooner when compared to the conventional wells. Click, please. So, okay, so what we are looking at here are 7 forms of artificial lift methods, and we have been using artificial lift, at least rod pumping, for almost a century or slightly over a century. Other forms of lift methods came sometime around middle of last century and thereabout. There are about 8 forms, even though we are seeing here 7. So starting from the left, we have plunger lift, foam lift, gas lift, and then we have lift mechanisms like rod lift, progressing cavity pumping, ESP. Hydraulic lift could be hydraulic jet pump or hydraulic piston pump. So I'm not including some of the other methods like velocity strings and such, but they are also employed. Then surface compression is another method, but That is not considered artificial lift, but it does help with the lifting aspect. We also understand that in terms of the motive power, the first three lift methods are primarily driven by what is available in the reservoir or formation pressure. Whereas the ones on the right four ones, or right five ones, I should say, from reciprocating rod lift through hydraulic lift, they all require some kind of mechanical device that is lowered inside the wellbore that is powered from the surface. So they are mechanical assistance. And in terms of the production rate, we can again subdivide these lift methods into different buckets. Lower producers, meaning less than 50 barrels typically. Higher producers are typically more than 2,000 barrels, and middle of the road. So you say that, okay, yeah, we understand all these lift applications, so why we are spending this afternoon talking about unconventional? Next slide, please. So what's the different now? First thing, unconventionals, please proceed. Yeah, so unconventional reservoirs, unlike the conventional reservoirs, are more like larger volumes. They are difficult to develop, meaning you require more technology input. There is a more cost component, as is shown in this technology pyramid from Dr. Holditch. Next slide, please. The second aspect, what we are looking at here, is from the Baker Hughes USA rig count. That is as recent as last month. And what we are seeing in the background, the purple outline, is showing how the number of rigs has changed since 1990. Rather than focusing on absolute number of rigs, let's look at the blue line that is on the top left corner, and then it is descending, which represents the number of percentage of rigs drilling for the vertical completion. And then focus on the orange or red line that is showing number of, or the percentage of rigs drilling for horizontal completions. And what we are seeing is that there is an inversion going on, with crossover occurring sometime around 2006, 7, 8 time frame, meaning the number of rigs working on horizontal wells, so-called horizontal wells, have exploded, and so has the number of wells. Next slide, please. And now what we are looking at is some data analytics work done based on this Rystad Energy's Naswell Cube product. And on the x-axis, you look at the different unconventional formations, like right from Austin Choke onwards. And there are 3 bars for each reservoir, each basin. And what we are looking at is the blue bar is the measured depth, red or the orange bar is the lateral length, true vertical depth, and then green bar is the lateral length. And what we are seeing typically is, with the exception of maybe one of the older basins, most of them have laterals that are exceeding 5,000 feet, almost a mile long lateral. And if we consider maybe about 10,000 feet TVD, then we are looking at about 2 mile deep and 1 mile on an average going out. So if somebody can visualize, then consider a straw which is laid across a football field, okay, 110 yards. So we are trying to produce from 4.5 inch completion or 5.5 inch completion through 5,000 feet length is equivalent to a straw which is laid across a football field. And that is the type of production challenge we have when we are trying to produce from these horizontal wells. Next slide, please. Now we are, let's look at some of the flow patterns that we observe in the wellbores. The graphic on the left shows flow patterns in the vertical wells. As the gas content increases along the x-axis, what we are seeing is that flow pattern changes from bubble through slug, churn, annular, mist, and so on. Now that is what we are accustomed to dealing with in the vertical or conventional wellbores. So in the horizontal wellbores, what we have is a vertical section as well as the horizontal section. So to understand the behavior in the horizontal section, let's look at the flow patterns in the pipelines that are typically observed. In this case, what we are seeing is gas quantity is increasing along the y-axis, and the flow direction is from left. Right? So what we are saying is the gas increases, gas which is shown here in red and that is shown in blue, is staying closer to the top.
John,
So,
we're having some audio issues. Perhaps you can fix your microphone a little bit.
do you hear me better? Hello?
No, it's still sounding pretty bad, sorry.
Okay, just a second, let me try to change something quick here. I'm afraid that may due to my here.
Thank you, everybody, for your patience.
So while he's adjusting his microphone, I'll remind you that after today's webinar, you'll receive a link to a recording. You'll get an evaluation form. Yes, are you back? Hello? You'll receive access to a recording of today's webinar, a link to registration, details for the class. All the webinars that we've been presenting in this webinar series are available on demand on the SCA website, and so you can participate in real time, or you can join us later at your convenience.
Okay, Susan, I'm back.
Great, thank you.
Okay, yeah, so sorry about that. So what I was talking about was that how the gas shown here in the red is staying closer to the top of the pipe, and the liquid stays to the bottom of the pipe, even though we are seeing bubble through, slug through, annular flow pattern. So now when we think of the horizontal wellbores, we are looking at the first part of the flow goes through the pipeline type of flow, and then the next part of the flow goes through the vertical lines. Next slide, please. Now what we are looking at here is we keep on talking about horizontal wells, but are the laterals truly horizontal? And as is shown in this graph from Rob Sutton, there are three different patterns. One is toe up, when the end of the lateral is at a higher elevation than the beginning of the lateral. Toe down, when the end of the lateral is at a lower elevation. And then what we call horizontal, or what is often referred to as a hybrid, is where the end of the toe may be, end of the lateral may be at the same elevation or slightly nearby the end of the lateral, but then there are too many ups and downs, or what we call a tortuous well path. So why that is important? Let's go to the next slide, please. So here we are looking at some flow pattern studies, flow pattern maps developed based on studies done at University of Tulsa Artificial Lift Project. On the left side, these two plots that you're looking at are the superficial velocities plot. On the left side, you're looking at 1 degree toe up type of inclination, and then you see two boxes, oil and gas. So these are typically flow conditions that we find in the unconventional oil and gas locales here. And what you're seeing is that for 1 degree toe up, meaning the flow direction is downward, most of the time the flow is in the stratified category. And when you look at the 1 degree toe, the second one is 1 degree toe down on the right. That is where what you're seeing is that for the same flow conditions, now the flow pattern is slug. So just a small undulation in the wellbore causes the flow pattern to change from slug to segregated to slug to segregated. And that's what we have seen this based on the measurements done inside the wellbore. Now, what we are seeing here at the bottom, the cartoon, is that because of such undulations, we will have areas where the gas would be trapped, typically attic section or slightly higher section, and then the lower valley sections is where we will see the liquid trap. So typically liquid gets trapped in between two gas pockets, and then when the pressure increases in the gas pockets, it blows the liquid out. And that is what leads to highly unstable, sluggy type of flow behavior, not in the lateral, but also in the vertical section. Next, please. Now, we are not going to see a movie, and my apologies to all in advance. Because of some technical issues with my laptop here, I'm not able to show, but there was supposed to be a very nice movie from University of Tulsa, experimental setup that shows how these flow patterns are changing with toe up, toe down geometry. But the takeaway from that video is that essentially what we saw in the simulation earlier is that as we go, even if we go 1 degree up or down, we are seeing significant flow pattern changes. Next slide, please. And here are some measurements. If you see at the two plots on the right, here are some measurements that were done in Eagleford wells, right? And what we are looking at is on the x-axis there's the time, and y-axis, excuse me, y-axis is the liquid quantity that was measured using multi-phase flow meters. So in case of well C on the top, we are seeing that there is a period of about 12 to 15 minutes when there's a very little liquid comes, followed by 12 minutes or so when there's a high quantity of liquid comes. And this is a type of flow behavior that causes a lot of surging issues with the pumping, primarily the artificial lift equipment that are designed for receiving more homogenized mixture. Now they are seeing a large liquid slugs followed by gas bubbles followed by liquid slugs. Not only that, we have surface equipment that are upsets because of the gas liquid separation issues. And then we have, of course, pressure monitoring and production monitoring issues also. Back pressure management also becomes a challenge due to this surging flows. One more thing I would like to point out here is that the periodicity of this slugging event is not uniform. In the same two similarly completed wells, we might see completely different behavior of slugging, and that is what is apparent here in the well A, that has a periodicity but with much smaller frequency, and it is not as well defined as well C. Next slide, please. So earlier slide talked about periodicity or the change in the flow behavior over a shorter time. Now let's look at what happens over a longer time period. And here we have three plots, again captured from some Wright Energies research work. And we are looking at in gas as well as liquid assets, how the production behavior for different operators. And it's a kind of average value. So what we are seeing here on the x-axis is the number of months of the production. So within 12 months of the production, within the 12 months, what we are seeing is that the production drops almost 50, 60, 70%. And then it flattens out after about a couple of years or so. So we are looking at variability in the production rate, not only over the shorter time frame, but also over a longer, medium to longer time frame. Now, this is something which we had not seen in the conventional before. Next slide, please. So, as a production engineers, as an artificial lift engineers, we need to be prepared for and plan for a wide range of production rate. And I should say not only range of rates, but also the phase quantities are varying. The phase fractions are varying, shorter term as well as medium to longer term. And that is where we have a major challenge with the artificial lift application. Next slide, please. We are also seeing some inflow phase distribution challenges because depending upon the type of completion, some perforation clusters, some fracturing clusters may not yield as much as was originally planned. As a result of that, we may have some inflow phase distribution that is not what was expected. And this has been proven using downhole measurements, basically fiber optics based sensing, as well as some flow meters. Next slide, please. So if we have to summarize the challenges, we are looking at deep, long, slender well geometries. And one topic I did not touch upon, it has been discussed often, is that there is an impact of this well geometry on the estimated ultimate recovery, or EUR. From the production perspective, there is a sluggy and turbulent flow, rapidly changing production rate, rapidly changing fractions, phase fractions, and uncertain inflow phase distribution. And that is what causes lots of challenges for artificial lift selection as well as application. Next slide, please. So what are the lessons that we have learned based on the things that we have applied in the field? Again, as I showed earlier, there are 8 forms of artificial lift. One form that has not been applied and that has been ruled out completely is progressing cavity pumping. And that has to do with the depth of application. So other than progressing cavity pumping, most all other forms of the lift that I talked about have been applied. So let's see what have been observations so far. Next one, please. So one thing is for sure is that we need to have some production engineers also, as well as operations people also involved when the decisions are made related to well design, particularly well geometry. And if we can have some toe-up orientation that can help possibly with the draining the lateral. Now that brings up some other challenges, but we'll not talk about those right now. Having a rat hole that will allow us to lower artificial lift equipment inside the rat hole that takes care of the gas separation issue also helps, right? Another one is that if we can control the tortuosity or minimize the undulations inside the lateral, that helps with this rapid phase fluctuations situation. Whenever we are changing the transition from the vertical to the horizontal section, if we can plan for it, if we can control it such that we have a flat section which is about 100 feet long, even though it is in the deviated part, if it's a flatter section, then we can land our artificial lift equipment, particularly the pumps, ESPs, rod pump and such, in that flat section so that they do not bend in the middle and cause the equipment not to perform properly. Next slide, please. During the early operations, people have begun to realize that choking the well seemed to help in the longer term. In the immediate term, we can give up some production, but in the longer term, we are improving the EUR, estimated ultimate recovery. And also we are, because of the choking, we are minimizing some of the facility upset issues, lift system management issues, because gas is not breaking out of the solution as much. So maintaining the liquid level also helps with keeping the gas more into the solution and not break out while the lift system is handling the phases. Next slide, please. I'll not be able to walk you through this entire table, and during the training session, we'll have a chance to go through all the details. But this is a very handy graph, handy table that shows how different lift methods are performing on different criteria, whether it is handling the gas or slugging tendencies, solids control, depth capacity, and such. Now, certain methods have, and as you can see here, there is not a single answer that performs uniformly across. And that's why we need to go over the details in like a session which is longer than this 30-minute webinar. Next one, please. So again, in general, the consensus seemed to be that for liquid-rich formations, gas lift, ESP seem to be the choice, as well as the jet pump seem to be choice when we have higher production rates. And then as the production rate starts declining, then people seem to be moving from gas lift to maybe rod pump or gas-assisted plunger lift, and so on. In the gassy production, when the liquid quantities are smaller and challenge is that of more of a removing the liquid or deliquification, then again gas lift is also useful. Jet pump is used primarily for fracturing fluid flow back in this particular case. And then plunger lift is deployed, and capillary injection is often used for injecting the foam or the surfactant, I should say. And in some cases, you can also use it for scale treatment and some other corrosion treatment and such. Next slide, please. As far as the deliquifying laterals go, mechanical pumps have some challenges because their intake, the way their intakes are positioned. The next one, please. And gas interference seemed to be the biggest challenge with the ESP, rod pump, what we call mechanical pumps. And gas lift seem to thrive on the gas, so we do not have those challenges with gas lift. So in this case, the industry seemed to be moving more towards the gas anchor type of solutions. And then there are a few other things coming on the market that basically help regulate the gas quantity that passes through. Next slide, please. So as I was saying earlier, if we have a straight section in the deviated area, most of the time people do not take the pumps into the lateral. Actually, I have seen very few cases where the pumps are taken into lateral. So if we are going to take the pumps intake as close to the reservoir as possible, then we would like to keep them in the deviated section. Then try to have a straight section. If you want to keep it in the deviated section, then try to keep it in a straight 50 or 100-foot long section where the pump can be landed. For most part, it is beneficial to keep it in the vertical section. In that case, having a rat hole type of completion really helps with gas separation. Next slide, please. Now, I cannot emphasize this particular part enough. Having a surveillance, continuous surveillance, followed by analysis of the not only the lift but also of the production is very, very critical for unconventional, because as we saw earlier, not only phase fractions but phase rates also changes in a very relatively short time. So having some kind of surveillance system not only lets us assess the health of the reservoir, but also help us prioritize the next set of tasks and also make quick adjustment as needed. So making this investment earlier in the life cycle, when the well is on the paper, even before it is drilled, is very, very important for unconventional wells. Next one, please. Let's skip this one. This one also. I wanted to cover some of the important lessons. That's why we are skipping a couple of slides here. So this particular slide captures all the lift methods and how they are applied during the different production phases. During the early production phase, when the production rates are high but rapidly declining, companies or the operators are typically using jet pump, ESP, and gas lift seem to be gaining a lot of favor amongst the operators, even in the basins where people have not tried gas lift before. And then once the production flattens out, somewhere around the middle, what we call middle to late production, then the rod pump becomes a preferred method. Gas lift may continue. In case of gassy productions, we can start with gas lift and then switch over to plunger lift, or and then also hydraulic piston pump has some application in deliquifying application. Next one, please. One thing we have to keep in mind is that as we have to switch from one to another lift method, we have to also keep in mind that we'll have to call some workover rigs for some lift changes like ESP to gas lift changeover or so forth. So if we can come up with a completion scheme from the very beginning so that we do not have to call the workover rig, that will not only help with lost production but also save some money. Next one, please. And here is one example of how the completion can be lowered with gas lift valves in place, and then the jet pump is circulated in. So initially well is unloaded as well as produced using jet pump. Next one, please. And once we are outside the application envelope for the jet pump, we can just circulate the pump out, close the sliding sleeve, and we can convert the valve into the gas lift without calling the heavy rig on the valve site and avoiding the associated downtime. Next one, please. So here we are seeing having a hybrid completion like this can be helpful. Next one. Let's skip this one. So going on to surveillance and monitoring, as we saw earlier, with such rapid changes in the production rate as well as pressures and phases, having accurate and timely monitoring is very critical for production management. And we cannot have just the snapshots like production logs, because they will give us just one time, whereas having a continuous monitoring, having some downhole gauges that gives us pressure, temperature in real time, that is essential for this. Now, just having those downhole gauges do not solve the problem. We need to have also a very good data visualization and analysis software. And in my opinion, that is where lots of work is being done and needs to be done whereby we can have a capacity or capability to digest all this data coming from downhole gauges. And more companies are moving towards that path. Next slide, please. Next slide, please. So what we are looking at here is one operator who lowered downhole gauges in 3 valves. And these valves are on rod pumping. And what we are seeing here is a production profile, pressure profile, downhole pressure profile. And as is typical, the downhole pressure drops very sharply. And having the permanent electronic gauge downhole gives us capability to adjust our production strategy. Now, one aspect that I want to point out here is when we zoom into the red plot for one particular valve, what we are seeing is that pressure fluctuations to the tune of almost 50 to 85 to 100 psi occurring in a very small period of time. And that is what is a typical sign of a slugging, downhole slugging occurring. So now visualize if you have a rod pump operating with this 100 psi fluctuations at the intake, meaning corresponding liquid and gas quantity coming in at the intake, Your pump is going to get flooded, followed by gas locked. And so having these downhole gauges can help us manage the speed of the pumping equipment so that it doesn't get gas locked and so on. Next one, please. Now here is another example of how having a surface flow measurement, multi-phase flow measurement helps. What we are looking at is a production test separators, typically costing upwards of $500,000 or so. And in a pad-based development, having such production test separators all over the field can be quite costly endeavor. Click, please. So what we are seeing here is that operator utilizing a multi-phase flow meter at the surface that can give you a very high frequency measurements of in real time of what is happening in terms of the production coming out, which is not possible with conventional production test separators that are shown on the left. So the plots that we saw earlier from 2 wells in Eagleford that were captured using this device that is shown in the right here. As you can see, it's a very compact, it is a skid mounted device that can be taken on the back of a truck that allows us to also test our wells with much higher frequency and in real time. Next slide, please. So to conclude this presentation, how the artificial lift applications differ for unconventional and tight wells. Well geometries, tortuosity in the laterals, that is what poses significant amount of production challenges in form of slugging that is occurring, changes in the phase fraction, changes in the flow, not only in the shorter term but also over the longer term. So understanding of this flow behavior is very important, and we still do not have complete handle on this. So we still need to work on it. Next one, please. And now at the bottom, you're seeing a couple of papers based on which this talk has been developed. So if you'd like to read more, then you may refer to those SPE papers. Now, what we need to do, as I said earlier, production guys needs to be involved during the well design phase. And somehow I was reading this JPT, not somehow, this morning I was reading Journal of Petroleum Technology, and there was this comment from the completions technical editor of JPT, and I'll read verbatim, quote, acceleration of drilling speed is leading to problems down the road with completion and production practices, both of which are huge drivers of the ultimate recovery. That itself says that how having the production guys during the well design phase can help not only minimize the production problems but also help improve ultimate estimated recovery. The second one is that we have to be flexible about selecting the lift systems. Not only our mindset needs to be flexible, but lift systems also needs to be flexible, and that's where vendor community is doing a lot of work. And we also, we meaning as a production practitioners, needs to stay abreast, stay current on what is being done now. Another thing we need to do in terms of flexibility is that we have to think a longer term at the same time while making quick decisions. By longer terms, we have to think in terms of the entire lift life cycle. What is my current lift that is most optimum? In 2 months time frame, what other lift method or what other equipment set I will need? In 2 years down the road, what lift? So if you are able to think longer term, then you will over the time realize which lift methods work best for your fields and how one can switch from one to another lift method. The last point I cannot stress enough, you need to include lift monitoring and surveillance right from the beginning. And that is where I would like to conclude this talk. Again, we can discuss, and we are going to discuss a lot more in detail all these aspects, including fundamentals on some of these lift methods in the 3-day session. So I hope you guys will be able to join. that. Thank you very much, Susan.
Great, thank you. I want to remind our listeners today that you can pose questions for Dr. Shotsky by using the question feature on the GoToWebinar dashboard there. If you have questions you'd like to ask him in real time, you may do so now. After today's webinar, you'll receive a link to the recording of this webinar if you'd like to share it with your colleagues. We'll have an evaluation form, and there will be registration details for the class, Artificial Lift and Real-Time Optimization for Unconventional Assets. And those are being offered in public classes in March in Houston and in October in Midland. Dr. Shotsky, I think you certainly endorsed using toe-up configuration for draining the laterals. What are the challenges associated with the toe-up configuration?
Okay. The challenge is, first of all, the drilling the toe-up. I'm told that it is a somewhat difficult one when compared to horizontal as well as a toe-down configuration. And during the production, what happens that the hill section tend to accumulate all the debris as well as the proppants that are going to flow back into the hill section. And in some cases, it is conceivable that the hill section may get completely clogged up, and we may not have sufficient flow passage through that area. Now, in the toe down, we have seen similar things happening at the end of the lateral, where all the debris as well as the proppants get accumulated, and sometimes people report that they lose part of the lateral as a result of that.
Great, thanks. Our next question: what do you think about subsurface compressor technology in unconventional wells?
I have heard about subsurface compression, and to my experience, I have not seen very many applications yet. There is definitely a scope for trying out some of this equipment. My thinking would be that the cost-benefit ratio is one thing that will need to be looked at very carefully. Another thing is that this subsurface compression technology, can it handle this large fluctuations, or does it also suffer from the same? But that is certainly something that we need to look into.
Great. The next question is also related to cost. Is there a comparison of the costs of the various lift systems that one might be able to use that would influence one's decision on which to select?
The cost is a bit tricky one because it varies a lot from operator to operator, even within the same geographic area, in my experience. But in general, the lift systems that requires frequent changeouts, they seem to end up being the costliest one. And that's why I focused on the aspect where if we can avoid calling the workover rig on the well site for changeouts, then we can save some of those costs. So going back to the question, it is very easy to say that, yeah, ESPs are the costliest because the equipment itself is costliest. But when you look at a particular well, if it is capable of producing higher quantities, then you are able to recover those costs also quickly. Now, one trend that I have observed is people are gravitating more towards the gas lift because it seemed to work relatively with less problems. Now, whether it is most efficient or not is a different issue. So plunger lift seem to be the least expensive because you do not have any external costs. If you have gas assisted plunger lift, that is slightly more expensive. So until and unless we take a look at a specific well condition, we cannot answer this question. And that's why operators are looking at the wells lift life cycle. Like some operators are saying that we'll go from gas lift to gas-assisted plunger lift, to plunger lift or intermittent lift, and so on and so forth. So we'll have to look at each field and particular operating companies' practices in order to arrive at the right mix.
Great. The next question comes from an engineer who has a horizontal shale gas well in late time, and he's asking it has more value to evaluate the J-curve rather than the whole nodal performance evaluation. He's looking really for the cheapest and most efficient way to evaluate a deliquification method for his asset.
Yeah. So the way to analyze this, I've seen that people are using different methods, and this webinar is not the best way to answer such questions because there are always pluses and minuses to each approach, and I do not want to give just one off-the-cuff answer. But yes, lift methods, like there are a couple of slides that I skipped that were specifically addressing a deliquification solution using gas lift in combination with foaming, for example. And how does one go about analyzing those, or at least understanding that? I guess we have to do that more in classroom context.
Great. You talked about continuous lift surveillance. How much does that cost, and what's the value add?
Okay, very good question. And this is something that I have always been asked for more than 10 years now, even in the conventional wells. And yes, it all depends on when you are talking about adding this surveillance mechanisms. When you look at unconventional unconventional well completion costs, reasonable value is 5 million. It is always more than that. And when you compare that to the cost of, let's say, lowering one downhole gauge, and don't quote me because I'm not selling the gauges, but it could be somewhere around $30,000, $40,000 or $50,000, depending upon the depth and the cable that you have to lower and such. Now that is, in my opinion, is very reasonable value. Now, when you add that to some of the surface hardware like a controller, and then you have to have some backbone, software backbone, and that is where we are not making enough investment. So the cost is always there and very easy to point out, but when you look at into the overall life cycle and what we can recover from it, I think they are very easily manageable, and that's why more and more operators are going for like continuous measurements like downhole gauges.
You also mentioned the advantages of being able to visualize the data and do analysis. Can you talk more about that?
Absolutely. So now, follow-up question after having the downhole gauges is that what do we do with all of this data? So when we go to the traditional way of analyzing our needs for artificial lift or doing the downhole nodal analysis or production analysis, typically we are dealing with one constant rate, and we are looking at continuous steady state type of condition. Where our current tool set is lacking is accommodating this stream of data that is coming from downhole gauges and how to integrate that into our analytical tools. So having the visualization, I mean, there are a variety of visualization tools, and you can do anywhere from MATLAB all the way through Tableau and quite a few others in between that I do not know even. But then once you visualize it, what do you do next? How do you use the current, whether you call it J-curve or nodal analysis? How do you do that in real time so that you can adjust the pumping speed in real time, right? Or you can adjust the injection rate and you can assess its impact. Those are the critical things that we'll have to work on, and they are being worked on, don't get me wrong, but they are not that widely prevalent yet.
Very good. I think we've run out of time for today's webinar. If there are additional questions that come from our attendees, we'll be sure to forward them to you so you can respond to them directly. And thanks to everyone for attending today's webinar. And as a reminder, you'll receive a link to the recording, an evaluation form, and a link to registration for artificial lift and real-time optimization for unconventional assets offered in March in Houston and October in Midland, Texas. Thanks, everyone.
Thank you.
Bye.